Hello, my name is Claudio Fuyu, and in this video I will briefly reflect on my final course project, which focused on the farmer's learning for autonomous trajectory tracking and dynamical obstacle evasion using a physical He-Wonder Ackermann robot. The project consisted of developing and validating an autonomous control system for a scale Ackermann vehicle on an F1 style Imola circuit. The robot was localized using a zenithal camera and an Aruco marker mounted on top of the vehicle. From this camera system, we estimate the robot's position and heading angle, and then they use that information to generate a compact state for the reformer's learning agent. The main objective was to train a soft-actor critic agent, or SAC agent, capable of controlling the robot by outputting continuous velocity and steering commands. In other words, the agent was not selecting simple discrete actions like left, right, or stop. Instead, it had to learn smooth control references for the physical Ackermann platform. For comparison, we use a classical baseline based on PID and pure pursuit trajectory tracking. This was important because PID and pure pursuit are much more traditional and predictable approaches for this kind of path following problem. The goal was not only to see if informed learning could work, but also to understand where it could be useful compared with a classical controller. One of the most interesting aspects of using reinforcement learning was how many design decisions affect the final behavior. The result does not depend only on the algorithm. It also depends on the state representation, action schedule, reward function, training duration, hyperparameters, safety limits, and how the policy is deployed on the real robot. For example, in our final SAC look-ahead version, the state included lateral error, heading error, velocity, angular velocity, progress along the track, previous steering, and three look-ahead angles. These look-ahead angles help the agent anticipate the upcoming trajectory instead of reacting only to the current tracking error. The reward function was also a very important part of the project. It rewarded progress along the track and penalized lateral error, heading error, excessive steering, steering variation, and unsafe behavior. The look-ahead terms also encouraged the agent to align with future points on the path. This made the reward effective for trajectory tracking and recovery, especially after deviations. However, one of the biggest lessons I learned is that training an agent and deploying it physically are two very different challenges. In simulation or in a learned environment, the agent can look stable, but on the real robot, there are many uncertainties. The camera has noise, the Aruco heading estimation can shift, the homographic calibration is not perfect, the motors and the servo have delay, and the robot does not always start from exactly the same initial condition. All these small differences affect the observation received by the agent. Because of this, reinforcement learning was much harder to deploy physically than the PID and pure pursuit baseline. The classical controller was more reliable for nominal trajectory tracking because it was directly tuned for the track. The RL controller could achieve successful runs, but getting consistent physical runs required many attempts and a lot of tuning. This was one of the most difficult parts of the project, but also one of the most valuable learning experiences, in my opinion. In the final evaluation, we compared PID and RL under two conditions, trajectory tracking without obstacles and trajectory tracking with moving obstacles. In the no obstacle condition, PID was more consistent and achieved lower RMS tracking error. These results make sense because the PID and peer pursuit baseline was specifically tuned for nominal path follow. Under moving obstacle conditions, the RL controller showed more interesting behavior. It reduced the RMS tracking error compared with the PID and also reduced the maximum tracking deviation. This suggests that the RL policy had better recovery behavior after obstacle interaction. However, the obstacle evasion success rate was more variable for RL, which means the agent still needs to improvement for consistent obstacle decision making. A major conclusion for this project is that reformer learning is very powerful, but it is not automatically better than a classic control. In our case, PID and peer pursuit were more reliable for nominal tracking, while RL showed potential for dynamic recovery under obstacle interaction. This means that a future improvement could be a hybrid architecture where PID handles stable nominal tracking and RL helps with obstacle-aware decisions or recovery maneuvers. The main limitations were sample efficiency, the sim-to-real gap, and generalization. The agent required several training iterations and many physical attempts before obtaining useful behavior. Also, the policy was validated mainly on the current track and obstacle setup, so it was not fully tested with many different obstacles, positions, speeds, or track layers. At the end, this project was very valuable to me because it connected machine learning, reformer learning, robotics, perception, and real hardware implementation. The biggest achievement was closing the field control loop, the camera feedback, state estimation, SAC policy, velocity, and string commands, and physical road motion. Even though the RL controller was challenging to deploy, this experience made me more interested in reinforcement learning and machine learning for robotics, because it showed both the potential and the real engineering difficulties of applying these methods outside the simulation. Thank you.